Hello, community. Today we're gonna code. Yes, a code session. And I asked myself, hey, what about coding? So, on LangChain 21 hours ago, the most popular templates Retrieval Augmented Generation chatbot and local Retrieval Augmented Generation bot. So, great, let's focus on this. You know, there's a new version of GPT-4 coming up. You can upload your complete PDF files here and extract the information without any plugins. We get a new cutoff date. We got a new multi-mode. So, taking into consideration all of this information, I ask you a question. And you answered and you said, hey, you're interested in some professional code implementation. How does it work with autocode? How does it work with Copilot or with GPT-4 Code Interpreter? Next was, you told me, hey, a lot of examples you have to pay for the OpenAI key, for the Cohere key, or you have to pay for different vector stores to get access there. That's very expensive. And sometimes you have some external no-code library where you have no idea what this thing is doing. And the question was, can we get rid of all of this and code it ourselves? And the answer is, of course. Another question was, can we have a complete coding tutorial? And it means really from 0 to 100%. And also the question, we integrate this here, some interactive user interface. Now, you know we have here Gradio or Streamlit, especially if we deal with LLM. I will go with Gradio. And final question from the side of my viewers was, hey, can we also have a final up and running app so that we can really see what's going to happen, so that we can play around with the code, we can modify the app according to our needs. And of course, we can do this. So here we are now. And today we will implement all of this, and we will build a domain-specific RAG-based LLM for a Q&A session, for a Q&A chatbot. And this is the first video, so this will be the easiest video, our introduction video to code. Now, before we jump into the code, let's talk about what we're going to achieve, what is our structure. I have a query, and I input this query to my LLM, and I expect a response. Can be a specific response in a text or in a coding exercise. So here we choose a Llama 2 model. We have a model has been trained but is missing the actual information, that the system has no information how to answer my query. So what we do, we go here to the main source of all information today. We go here to the internet and we will find here our pages where the information is in real time. And we will use here RAG to parse the HTML content, extract here in the first step the textual data. We chuck the text into smaller pieces based, for example, in the simplest version of the character count on the overlap. And of course, then we embed here all this information in a new mathematical space, in a vector space. And we will use here the sentence transformer for this mathematical mapping from the semantic space to a mathematical space where vector represent the semantic similarity of our sentences. Just to give you an idea, let's say we take now, or we borrow here the content from 1,000 internet pages. We have about 100,000 sentences. I only have one input query, so we have to find here the answer to this my query in those 100,000 sentences. We use here a cosine similarity in a vector space to get the top 10 answers. And within those top 10 answers, we will re-rank this and to the best 3 answer. And in the end, we feed back here to our LLM a very specific RAG optimized generative AI prompt, an in-context learning prompt. So we have the latest and best and most useful information that the system feeds back in the LLM, and the LLM will generate here a beautiful answer. Okay, so yeah, we will create an index, we will re-rank the results, we will use here also something from the sentence transformer, which is called a cross-encoder. And I will show you how to create here an ICL in context learning optimized prompt that is RAG based. this with feedback, and this we will get here then the result. I was asked, no LangChain, no LLamaIndex, no vector store. Can you show us here a simple code exercise without any external helper function? We want to code this, and here we are. We are gonna code this. Of course, cherry on top, we will use here an interactive user interface. We will use Gradio here. So you have this up and running. You can send the HTML link to your friends, and they can try it out themselves. Now you know me, so what do you think about a little challenge? Let's do something new. Now you have access to ChatGPT for free, so I was asked, hey, can this be our code generator? Yes, of course. We want to have fun, of course, and some insights into the flow of coding, how we structure this. We will not work here on a Colab or on another Jupyter notebook, but hey, I discovered there's something beautiful like Hugging Face spaces that we can generate, we can program, we can apply here from a Docker to a Gradio. We will work today with Gradio. There's the new version 4. You can publish your result as an interactive demo. And in the result of this video, we have built a new interactive AI system where our external knowledge here is the documentation, the official Hugging Face documentation of the parameter efficient fine-tuning. So we build ourselves a coding AI. And you might ask, why? Well, in the next video, we're gonna use this coding AI for the next step. Remember, this is the simple version, just to give you a feeling. We will follow here our Hugging Face wizard and syrup. This is here the expert knowledge we will access today. And if you go to, for example, GitHub, you see under Pacman 100, we have here all his GitHub repos. And I'll leave you the link in the description of this video so you have access to the files we're going to use and you can download it here, either from Hugging Face or from GitHub. The first step, we always start with the data. So from our internet, we have to generate the data for our specific query. Then we do a little bit of RAG engineering with an ICL prompt optimization. Then we have here a run of our Llama 2 model with a RAG. We have an inference, and we build here the interactive shell around this, an interactive Gradio user interface. Those are our 4 steps we're going to do today in this video. So let's start with number 1. We borrow from the internet some real-time content from specific web pages. And remember, this is the easy solution. So we now go here and we tell the system, hey, please go to Hugging Face to this web page, to this manual where PEFT is explained, where we have the complete AI or the API description, and load here all those information from the official Hugging Face pages explaining what PEFT is. So at first we are a single domain, but of course you can have multiple web pages and go multi-domain. And here we go. I built here on a ChatGPT conversation from a Hugging Face wizard. I leave you the link in the description of this video, and we just continue and follow his path. So he said to ChatGPT, hey, how do I scrap here web pages? Can I use Scrapy? And ChatGPT comes back and says, hey, this is a powerful and flexible Python web scrapping framework. Here's a step-by-step guide how to use Scrapy. So you install it with a simple pip install command. You create a new project. You say, hey, my project, for example. You define a spider. A spider is a class that defines how to scrape a website. In this example, yes, we go to this one. And you see, and now ChatGPT creates the code. You have here the specific class here of spider. We have here our URL. We have here the parse command. Then you run the spider. And it's time to run the spider, navigate to the yes, yes, yes. And you have here a simple command. Says that's it. You've successfully used Scrapy to scrap data from a website. And then the user comes back and says, hey, update the above code to use BeautifulSoap for the parsing. ChatGPT comes back, says, of course, integrate BeautifulSoap here into a parsing instead of Scrapy built in CSS selectors. So at first we have, of course, pip install BeautifulSoap, and then we simply update here the code, and we have here, where's our BeautifulSoap response here, our HTML parser. And it explains what it did and says, great, beautiful. Now the human user says, hey, I want the parser to ignore any multimedia data on these internet pages, such as images, videos, or audio. So he's just interested here in the textual description and the textual code, and save the content converted from HTML to text into a file whose name is simply the hash of the URL being parsed. Output the code for achieving this. And now ChatGPT comes back and does exactly this. Save the content, text content to a file, and go to the next page link. Beautiful. So explains what it did. The file name will be something like beautiful.txt, where beautiful is simply a specific hash of the URL. So then the human says, hey, can you write the code to scrap here now from Hugging Face here from the documentation here, a specific parameter efficient fine-tuning methodology using the steps you outlined above. Iterate over all the sublinks also in the file. And then ChatGPT comes back, says, great. So I just adapt now here and I build now for a specific internet address here, my Hugging Face spider, for example. So calculates the hash, saves the context to a file, follows all sublink. Beautiful. So you see, this is done by ChatGPT. Beautiful explains what it did. Great. And now the user says, hey, for sublinks, check that they're really from here, the documentation pages. Comes back and says, okay, let's do this. Update the code. Beautiful. Updated code is valid sublink. Okay, you check for this. Tells you what to do. Now, next instruction for the human. So you see we build up step by step, level by level. Write the file to an output folder. Let's call it output. Make sure to create the folder if not already present. Have this in the init logic of the scrapper. So here we go. This is done. Yes, yes, yes. Then next command is add logic to not parse any multimedia, such as images, videos, or audio. We do not go here in the third step to multi-modal. We just want to have here extraction of our text. Says okay. You can check here the MIME type of the response content before extracting and saving to the file. And if you have a look at this, where are we? And as you can see here, we define here is multimedia content, and we define here one of those image, videos, or audio classifications. And then we say here in the parse command, hey, for the logger, skipping multimedia content for this specific URL, if given that this is one of those three definitions. Beautiful. Filter only the text from here specific elements with specific values, then comes back, says, okay, let's do this. Where are we? Here we go. Filter only the text here from the div elements with the specified class, group, or soup select, and the code is provided to us by ChatGPT. Updated code, soup select, CSS select, yes, find all elements with the class attribute. The rest of the code remains the same. Beautiful. In a further definition here of this function, now write a function to chunk text based on two parameters. Now, normally we use here the sentence length, but if you have extraordinary long sentences, you need some other idea, some simple idea. So you can just define here the chunk length. So the maximum length of each chunk based on the number of characters. and the overlap, so the overlap of text between the consecutive chunks. And ChatGPT writes here now with the two additional parameter, chunk length and chunk overlap, into our program. Beautiful. And we have here the example, chunk length 40 and chunk overlap 10. Go with whatever is suited for your particular text. And explains here, we iterate over the text, starting from the beginning and incrementing by the chunk length minus chunk overlap in each iteration. We extract the chunk of the text from the starting index to the ending index, and then we append the chunk to the chunks list. Great. Now, the next further specification is, hey, use the above function to chunk all the files in a given specific folder and create now a panda data frame. A panda data frame is something beautiful with the following three fields: the ID, the content, and the file name from which the chunk came. And of course, create here panda data frame. Yes, beautiful. And you see the code is generated. Process file here, and then we have here panda data frames. Great. And you can, for example, display here an example of this panda data frame. Additional command, create a script for the above code, taking in 3 arguments: chunk length, chunk overlap, and one is missing, the folder path. Okay. Says, okay, let's create a script that takes here the chunk overlap, the length, and the folder path in, will process all the files in the specified folder, chunk their content using the provided parameters, and create a panda data frame with the required fields: ID, content, and file name. And then here ChatGPT writes the code for us. And it tells us, hey, to run this script, can't be easier. Just open your terminal or your command prompt and execute the following command. And this is it with your specific parameter, with your desired values. Okay. And then we say, okay, please here use some specific for handling here the script arguments. Save now the output data frame here to an optimized file format. And we go here with a Parquet file, and whose path is a script argument. And so we just convert here panda to Parquet. This is done. Beautiful. Overlap, yes, yes, yes. And then we have here a panda data frame. And then we simply say data frame to Parquet file. Everything is included. This is an easy task, and we have now a Parquet file. And this is exactly where we then can start off, since we now have the data in a file format that is optimized and the right way to go with a Parquet file. ChatGPT comes back and says, hey, you just have to run this. Just type in script name.py and your parameter, and you're ready to go. So now we have all the data, the textual data, at first in a panda frame, and now we have a Parquet file, beautiful and optimized file format. And now comes the part where we will use now here to get here or make this transformation here of our, let's say the chunks are our sentences of the text. And now we transform the sentences to a vector representation in a vector space. We call this the embedding function. And we use here a sentence transformer and an sbird to get the embeddings of a sentence. So you see, I don't need any vector store, any chain at all. We just use here the good old sbird multimodality. So at first, we install here our sentence transformer library, and I have more than 50 videos on my channel about sbird. So please have a look if you have any question about how to apply sentence transform and optimize them. Very easy. At first we say, hey, let's do something like get sentence embeddings. So we just call here from Hugging Face a specific sentence transformer model that is available on Hugging Face. And if you have a look, they, for example, go here with a bird model, with a smaller bird model. It's called Distill Bird Base Model with the tokens. And then we just say, okay, now encode the sentences to get their vector embedding representation. So we say model.encode the sentences and return now the embeddings. So what it does exactly here, it takes in a textual sentence, and returned is a numerical representation in a vector space where we can operate with a cosine similarity to find semantic similar sentences. Beautiful, this is the code. There are about, 50 to 100 different BERT and SBERT models. Please go to sbert.net and choose the best model for your specific task. Yes, explains what it does. Great. Yes, input file and output file. So we say now, okay, now create a script that takes in the following arguments. We have an input file where we have the text chunks created just 1 minute ago, as I showed you, here in our Parquet file, a file with the Parquet extension. And then we want now an output file, having here the bin extension to save the output search index. So what we do, read the input Parquet file using the pandas. You remember we have 3 columns, the ID, the content, and the file name. Then use here the specified sentence transformer function from above to embed each sample and create an index mapping from unique numerical ID to embedding using here a specific index library functionality, and save the created index to the output file. Great. ChatGPT comes back, says, hello, I'm ready to do this. So we use this, we read in the input from the Parquet file. We use our SBERT to embed here all text chunks now to a vector embedding. And I will create here the code that a search index is created. You see, you don't need any vector store or anything else. You do not have to pay for them. It is so easy to do it yourself. And this is the beauty, because also we pretend we do not know how to code. ChatGPT is giving us here the complete code structure. And later on, I will show you we can use GPT-4 to even improve the code further. But this is the first video here of this video series. So we go with the basic model. Sentence transformer word base. Great. So here we have now a function to create here the specific index. And this is here a library. Maybe I have here an interrupt and I show you this specific library. And then we have our main function, input file, output file, reading the Parquet file, get all the embeddings from the text chunks, create now the index that we have, save the created index to a new output file, and this is it. We are ready to go. And here, ChatGPT gives us the command, hey, just run here, create here the index, and this is it. So we have now a script. We'll read the text chunks from the Parquet file, embed them using any sentence transformer of your likes, create an index, and save the index to a file. So these 2 files we need now in the further computation. So more or less we can say, hey, this is great because now we have the data preparation and the cleaning data phase ETL more or less done. Here is another command by the human user says, hey, load the save search index and write 2 functions for creating embeddings of a given query. Because you remember, we have now just the text converted to a mathematical vector representation, but I started with my query to my LLM. And now to have a cosine similarity, now from my query to all the text passages, we have to have now also that my query that I have to my LLM will be also transformed in a vector representation. So using the search index and query the embeddings, I now find the, let's say, 10 nearest neighbors in the vector space. So if I have my query now in a vector, I look for the nearest vector representation here, or the 15 nearest vector representation. And this is very easily done in a vector space. ChatGPT comes back. Yes, of course, let's do this. So you know this, we create the index, we load the index. we have here our query embedding. This is happening with the command, model.encode, here the query. We return now the embedding, and then we have simple function here, find the nearest vector neighbors given my query. So find the best 10 answers in the very close by vector space. So find the nearest neighbor for the query embedding. And we have here just we utilize here a Python library. Great. So again, the main file here, read in our package, create the embeddings, create the index, load the index, create an embedding for my specific query using a sentence transformer. Of course, the same model that we used to convert here our internet text content to a vector embedding. Find the nearest neighbors with this specific definition, and then you print out the result. And you say here, even some chunk content, the distance, and you can even have here a confidence level or a close by metric relation, but it will give you here, let's say, the best 5 results. And this is now the best 5 results answered from external data that we can feed in now in an in-context learning. And this will be an additional part to our prompt, to our LLM. So we have achieved a complete RAG process in this simple line of codes. We did not have to know anything at all about Python because ChatGPT did everything for us. It explains this great. Yeah, in addition, you can have now an ID to check the dictionary and use it to get a list of the retrieved text chunks and put the logic in a function. So let's do this. And of course, perform similarity search. Yes, you know this now for 5 neighbors. So we have our key file, we have our embeddings here. We create the index. Yes, yes, less. You know this now. Create here now ID to a specific dictionary. And beautiful. So with this latest version of the script, we have added the perform similarity search function. So this vector operation in a mathematical space that is so much faster, and it is beautiful to find semantic similar content, which performs the entire similarity search process. It returns then here specific dictionaries where the keys are the chunk IDs and the values are the retrieved 5 or top 10 text chunks. If no query is provided, okay, yeah, use the return to print the result. And when you run this now with your specific parameters and you define the 5 or the 10 nearest results, this is done. Now, empirical data have shown us that this cosine similarity in a vector space is not the optimal way we can do this with an expert system. Because to our bi-encoder expert, we also have a cross-encoder expert. I have a specific playlist with 5 or 10 videos how to use cross-encoders on my channel and how to optimize cross-encoders. Now we just say, hey, we need to improve here the ranking of our return results from the external data. And to get a better and an improved ranking, we use now an expert cross-encoder to re-rank here our results. Yes, yes, yes. So in the sentence transformer library tells me ChatGPT, we have the cross-encoder class. Yes, ChatGPT had a look at my videos from about 1 year ago. The cross-encoder model takes pairs of text segments and provides here now a single evaluation score indicating the relevance of the second segment to the first one. There are specific training data set that provides here our cross-encoder with this functionality, with this precision. And remember, if you have a specific domain knowledge, like I work in physics and mathematics, I trained my own cross-encoder on my specific data structure. on the specific physical, chemical, biological names, specific mathematical terms, to have the optimal vocabulary, to have the optimal encoding structure. So I have here domain-specific cross-encoder. If you want, have a look at one of my videos. So we have the result to re-rank now the retrieved chunks by our cosine similarity with a better and more performant algorithm. So again, cross-encoder are with our S-word, our sentence transformer, and we update now here simply the similarity search function. Let's go there. So here we have our re-ranked chunks with now a cross-encoder. So create a list of tuples, each containing here this query chunk pair, get the scores for each query chunk pair using the cross-encoder. So if we have now the top 10 query chunk pairs, we get now, if you want, an evaluation, an additional evaluation on the quality and a re-ranking of the top 10 answers. So you sort the chunks based on the score now of the cross-encoder in a descending order. Beautiful. Yes, yes, yes. Index query. Yeah, you know this now, and then you have the result. So in this, again, updated perform similarity function, we use now the cross-encoder class from the sentence transformers from SBIRD to load here a pre-trained cross-encoder model. I hope it is domain-specific and you trained it on your specific domain, so you can fine-tune here also the cross-encoder. And of course, you can fine-tune the sentence transformer. So you see, you have multiple approaches for fine-tuning, for optimizing your system, but more about this in a later video. And then you use simply the re-ranked chunks with the cross-encoder function to re-rank the top 10 results. And now you have not top 1, top 2, top 3, but you have maybe top 2, top 4, top 6 here as the leading and best evaluated retrieved chunks from our external data. The script will re-rank the retrieved chunks using the cross-encoder model. Beautiful. So here is now where here the official Hugging Face documentation that created this code ends. Here I will leave you the link in the description of this video. And then I just uploaded it here to my account. And as you can see, we are here default GPT 3.5, our ChatGPT. I uploaded it and I was interested if I can continue. And I said, hey, please summarize and explain the complete conversation in this session. And I was hoping that bringing this conversation in, it's more than a month ago, is now here ChatGPT able to have here a summarization of all of this, what I just showed you. And it comes back and says, certainly. In this conversation, the user started by asking, yes, you know, we have been through this. And then, yes, yes, yes. Code example, explanation, step-by-step instruction was provided. Request, including web scraping, text chunking, data frame creation, the search index creation, similarity search with our SBIRD, and then re-ranking with our cross-encoder model. So you see, if you have here those chats available, even here our Hugging Face wizards, they show you unbelievable here. If you do not know how to code or you encounter a coding problem, hey, ChatGPT is able here in this case, for example, to do here the perfect data preparation. And now we have here different files. We have created an index. We have created all our embeddings, and we even have a cross-encoder. Isn't that fantastic? And we're going to use this now, because now we're going to enter here the RAG coding, and we will now bring here our LLM and our RAG-based new external data together to form here an optimized in-context learning prompt engineered structure. So part 1, data preparation, check, finished. Next part. Let's code now this exercise in a new space. And I really mean in Hugging Face I logged into Hugging Face, said create a new space for me. So, and I say here, this is my LLM rack license. Yeah, and I go here with Gradio. So as you can see, my hardware requirements, I just have a CPU basic. If you put in your credit card, you can go for whatever you like, and you see here the prices. So you can go even with a 184 gigabyte VRAM. So there is enough power for any application that you would need. I will go here with private because I show you here the way forward, and then the final space. I give you also the link then for the final space by our Hugging Face wizard. So this is it. This is all we have to do. Let's create the space. And so get started with your Gradio space. Yes, beautiful. But I want to do this here very slowly, very precisely. So I go here now, Hugging Face, and I create now here on Hugging Face space here my application, my Python file. Commit directly to the branch. Yes, beautiful. And now what I'm going to do, I'm going to insert here the complete code, and you will recognize this code. So here we go. Edit, and let's just insert here now the code. And let's start to understand what is happening here. Oh yeah, we have now, of course, to upload here now our input data, the two files that we created. So how we do this, easy, we go here to files. And as you can see here, I just empty readme, and here just the application. But now I want to add here the files that we created with the other code. And let's just say upload the files. As you can see, I have here my Parquet file uploaded, and of course here my embeddings. So commit directly to the main branch, commit changes. Yes, let's do this. And now if we take some time, now we have here our Parquet file here with the chunks, and we have our embeddings. And yeah, maybe we should do here for the dependencies a requirement txt. Let's do this. Create a new file. You can do this here. So let's see what we need. What we need on dependencies. We need our sentence transformer, our Esper.net. We need here our index generator. We have to go to the hub. We need SciPy, we need NumPy, we need the pandas. We need, of course, everything about Hugging Face transformers. And we will use something beautiful by Phil Schmidt. It is called Easy LLM, and where we can switch here between, for example, OpenAI embeddings and BERT embeddings. This is something I show you in the code. So let's say this is it. This is our commit. Say that's it. So if we go now here, we have our requirements, our embeddings, our Parquet file with the data. Yes, you can write a beautiful README file. And here we go now to our applications. Now we go here in Edit. And let's have a look what we have. Well, as I told you, we have our sentence transformers, where we have our bi-encoders, our SBERT system, and our cross-encoder. Then we have our index generator, NumPy. Then we have here as a user interface, I will use Gradio. If you want, Streamlit is also another beautiful opportunities. We go with our workhorse of pandas and Torch, great. As I told you, our easy LLM here, our helper is there. And from the Hugging Face transformer, we have the tokenizer. So prompt builder is Llama, yes. Then you have here your specific Hugging Face token. Remember, you have to insert your right token here. Then you define the max new tokens, the default max new tokens, and the embedding dimension. Search index file, the embeddings we just uploaded, the Parquet file, and the cosine threshold for calculating the cosine similarity in your vector space. Then if you have here an NVIDIA GPU, you take care about CUDA, or you say just CPU. We will run only on CPU. And then we go here with our models. As I told you, Our LLM here is a Llama 2 70 billion jet Hugging Face optimized model. Great. But please remember, for this you have to go and get here the permission by Meta AI for the Llama 2 weights and everything. So it's not really an open LLM, but never mind. And then here for our RAG, we have here our bioencoder from Sentence Transformer. We use here this specific model. And for our cross-encoder, we go here with our mini language model that has been optimized on the MS Marco dataset. Beautiful. Our tokenizer, of course, from the pre-trained model ID from our Llama 2. And this is it. Now we have defined our 3 models we're going to use. And now we just have to create here the interplay between these models. And of course, we need to create now a question and answer prompt. Yes, yes, yes. Create some condensed question prompt. So given the following conversation and a follow-up question, rephrase the follow-up question. This is just here some, if you have the chat history, some optimization. Yes, then get the prompt. Beautiful. You know this. Get input token length. Here we have now from Phil Schmidt, as I told you here, a specific code completion. As you see, you put in your temperature, your top K, your top P, everything else you can go. Then you load here the index where we provided here the index files already. And then create the index for the PEFT docs from the NumPy embeddings and avoid the arching mistakes when creating the search index. You notice this we have done already on my videos. Then you simply create here the query embedding, as I just showed you here with our bioencoder. Then you find here again, here the same code, the next nearest top 10 neighbors, and this is it. Then you use here the cross-encoder to have here the fine-tuning of our top 10 ranking. And you get here the optimized fine-tuned methodology. And then finally, we can have here our generate here the condensed query. And yeah, you notice the interplay between the human and the assistant. And the system prompt here is, for example, please insert what you like. You are a helpful, respectful, and honest assistant. Please answer always helpfully and possible while being safe. Your answer should not include any harmful, unethical. You notice this is clear. Description, what we call it a PEFT-based documentation, question and answer chat-based, based here on a Llama 2 70B model. Remember, for Llama 2, there are specific legal requirements. Yes, yes, yes. If no torch is available, just say, hey, I'm running here on a CPU. And then we have here clear the text box, because we are already working here on the Gradio user interface. You know this. Measure system iterator, yes, query embedding. Now everything comes together, beautiful. And you define your output. Process example, check input token length. If it is too long, gives you a warning, beautiful. Then what we have here now, we load here our 2 files. You know, we have here now the search index, and the second is here the read the parquet file here and a panel data frame. Beautiful. And this is it. The rest now is here absolutely just the Gradio commands. With the Gradio blocks in a specific style, we have markdown, we have the group, we have our row. You see, we have here the retry button, the undo button, the clear the input button. And then we have here an accordion where we have our advanced option where we can say, okay, the maximum new tokens, or you define here on a slider your temperature. You define here the top P or the top K parameter. Of course, you can provide here for the demo some examples. So the user just clicks on it and gets this as the input string. Yes, yes, yes. Success, generate the output button, event, pre-process. Yes, this is Gradio only. Retry to click. Yes, beautiful. This is just here for our Gradio user interface. And this is it. This is it. And you might say so. And now you just go here and runtime error. Let's have a look at this. Add the app and you get here. Yeah, of course. If you click now on the app, you will see it if you input your Hugging Face token. So if I insert my Hugging Face token, here we are now. We are building, as you can see, in real time. Takes some time. Okay, let's see. Okay, so everything is loading. Beautiful. This looks interesting. Yes, we are moving along. So yes, downloading everything that we need. Beautiful. Okay, there is no problem. The above exception. Okay, runtime error. Great. What is it now? We look here. You're trying to access a gated repo. Llama 2. Do I have permission to access the Llama 2 model on Hugging Face? Are you joking? Is this really a thing in November 2023? Wait a second. Okay, here. Yes, look. Cannot access gated repo for Llama 2. You request to access the Llama 2 model. I still have to, I have created a new account on Hugging Face for this video. And my email is now, I must request from Meta a new permission that I'm allowed to use Llama 2. So let us go to the official PEFT Docs Q&A chatbot, print a LoRa config demo, and here you have it. So you see, this is exactly what you get. You get an explanation from the manual here, from the API, and you have here also some code droplets. It explains how you can configure your PEFT model. You can say, hey, print the code for the LoRa config. Then you get a shorter explanation what this is all about. Takes a base model, a configuration object as an input, and returns a trainable PEFT model. And then you get here, as you can see, a simple Python code. So you do as always, you have your transformer, you have your PEFT, you set up the LoRa configuration. Yes, this is exactly here the following parameters that I already showed you. And then you have here the base model. We take here T5 base model, and then you wrap the base model with the get PEFT model function to create a PEFT model. Beautiful gives you also some additional further information. You can customize here the LoRa config object to adjust the scaling factor, the dropout probability of the LoRa layers, or replace it with a different PEFT method if it is desired. For the user interface, just to be specific, here you see, here we have the advanced option, as you already saw, the system prompt. You can put here your personal system prompt, whatever you want the system to behave, the maximum number of tokens, the temperature of the system, the top P and the top K parameter given within a specific range. You have here some examples. How do I use LoRa with custom models? You see it's in there. You just say submit and you get an answer. So we have here more or less a complete here Gradio user interface. And you see, how can I use it? You instantiate a base model, create a LoRa config, wrap the base model with get PEFT model to get a trainable model, and train the model as you normally would train this. So you have here 1, 2, 3, and 4 steps exactly how to do this. And you can ask the system also question and explain its specific term. So there you have it. Now, as an outlook to the next videos, remember that we can optimize ChatGPT code, Python code, for example, with a specific configuration that we will apply here for GPT-4. So GPT-4 will tell us how good is our code, how we can optimize our code. I would like to make a video about this in the next upcoming videos. Of course, as you said, we can have here the data from our real-time internet data, and instead of providing those data with here a rack-based API, we can have, if we have the data, we can use the data to fine-tune here our LLM. And if we do not have an extreme compute infrastructure available, we will not go with fine-tuning. This is very expensive, but we will use here the parameter efficient fine-tuning for our LLM with the new data. And maybe I show you some parallelization optimization, how we can do this. So instead of using here some external data and just use here the method here of rack-based, we can of course here also fine-tune and parameter efficiently fine-tune our LLM with the new data, which has a big advantage because now our LLM has been trained on this data and is able to make some logic deduction, maybe even some reasoning on the data, while if you just focus here on a rack-based API generation here of an answer to my query, we just feed here specific information to the AI within our prompt, but the system does not really inherently learn this information. So this is the outlook for the next videos. I hope it was informative, and it would be great to see you in my next video.